Let's begin with the first subject, namely graphs and graph traversal. Imagine a set of entities. That could be cities, people or change sets in a version control system such as JIT or Mercurial. There may be relations between these entities, for example roads connecting the cities, relationships between people or parent-child hierarchies of the version control system change sets. The entities and the relations between them constitute a graph. We will refer to the entities as nodes and to the relations as edges. In this case, the graph is undirected, which means that its edges have no direction and that we can traverse it in either direction. Sometimes edges can be directional or directed, and then we can only follow them along the arrow. A directed edge could correspond to a one-way road. When edges are directed, it may make sense to have two oppositely directed edges between two nodes. This corresponds to having two oppositely directed one-way roads between two cities, perhaps separated by a crash barrier. A graph with directed edges is called a directed graph. And last, if we travel along a path in the graph and arrive at the same node we started at, that path is referred to as a cycle. That was a bunch of terminology, but the important thing here is just to notice that graphs can be used to represent all kinds of things. For example, various kinds of networks such as computer networks, roads, and relations between things. One especially interesting kind of graphs is called trees. A tree is simply a graph without any directed edges and without cycles. If you flip it upside down, it becomes obvious why it's called a tree. Trees generally represent hierarchies such as parse trees or nested lists. So that was graphs and trees. They only become interesting, however, if we use them for something interesting. So let's proceed. Here's a graph which could represent a real-life data model. Often it becomes relevant to traverse all nodes in a graph, either in order to search for a specific node or in order to print out the graph, or serialize it and store it to disk. One way of doing so is referred to as depth-first search, or just DFS. DFS can be thought of as a curious strategy in which we continue our exploration on the latest visited node first and wait exploring new connections from the previously visited nodes until the latest findings have been fully explored. DFS is often the traversal strategy of choice, and maybe that's due to its easy implementation using recursion. We will see that in a moment. We will now traverse the graph with a depth-first search and put a number on each node corresponding to the order in which the node is visited. Let's begin the traversal by visiting the first node, A. From node A there are two edges, to B and C respectively. Whenever we choose one of these nodes, we need to come back and explore the other node later on. So the nodes should be remembered, but in a way that newly visited nodes will be recalled before older visited nodes. For that we will use a stack, which is just like a stack of paper. Things can be added to the top of the stack and popped from the top again in reverse order. So here we will add B and C to the stack. Now we need the next thing to explore. So we pop the top element from the stack, which is C. C is now number 2, and from C there is an edge to E and F. And these are both added to the stack, done with C. Next node is popped from the stack, and this is F, which becomes number 3. F reaches 3 nodes, namely G, H and I, and these are all added to the stack. And next node to visit is I, which becomes number 4. I is not connected to anything, so we will just proceed with H, which gets number 5. H doesn't have any connection, so we continue to G, which gets number 6. There are 2 outgoing edges from G, namely to D and E. These are added to the stack, and we continue our traversal to E, which gets number 7. E has no outgoing edges, so we continue to D, which gets number 8. D connects to G, but G is already visited, so we will not go there again. In a case like this, where we could end up visiting the same node more than once, we would perform some kind of bookkeeping of which nodes that have already been visited, either by setting a flag on the nodes themselves, or by storing the IDs for the visited nodes in a hash table. For remember, from the previous module we learned that hash tables both provide constant time insertion and lookup. The next node on the stack is E, but E is already visited too, so we do nothing when retrieving it from the stack. The last element on the stack is B, which gets number 9. Now the stack is empty and we have made a complete traversal of the graph. Let's take a look at a concrete situation where such a depth-first traversal is useful. For a given node, depth-first search first explores a given child node and all its descendants before proceeding to the next child node of that node. So this only says something about the children, but what about the children's parent node? Should that be handled before or after the children? Both strategies make sense. Let's have a look at each of them. If the parent node is handled before its children, the traversal is referred to as pre-order. Applications include printing hierarchies like the one you see here, which could be an organization of groceries in a grocery store. Here is a code snippet of a pre-order traversal that can print out a tree structure with some nice indentation. It takes a node and an integer representing the indentation level as input, and in its body, the node's value is first printed with a whitespace prefix given by the level variable, and then it calls itself for all that node's children, but with an indentation level that is one larger because the children are one level deeper in the hierarchy. So first the value is printed and then the children are handled. Let's try to execute the method on the tree seen on the screen. Here are some lines to visualize the indentation levels. We start at the top level node and print its value with indentation level 0. Then we explore all its children and increase the indentation level. The first child is meat, which is printed immediately before we proceed to its children while increasing the indentation level again. The first child of meat is chicken, which is now at indentation level 2, and that node has no children, so that can be considered done. Back to the parent, and proceed to the parent's next child, beef, which again is at indentation level 2. That node has no children either, so we backtrack to meat, which is now also done, and proceed to the second child of the main node, namely vegetables, with indentation level 1, because main had indentation level 0. That node is printed immediately, and we proceed to its first and only child while increasing the indentation level. Frozen is printed immediately, and then we proceed to all of its children, which are peas, beans, and spinach, all with indentation level 3. That was all nodes, and we've now got a nicely printed nested list to the left representing the tree structure. In pre-order traversals, a node is handled before its children. In contrast, handling a node after its children is referred to as post-order traversals. Here you see the same code as before, but the node value printing has been moved below the child node handling, and the code is therefore now a post-order traversal. While pre-order traversals were useful for printing data hierarchies, post-order is useful for executing hierarchies. The tree structure on the screen represents the expression that is written here. Another example of something to be executed could be a database query execution plan. Of course, the values that a given operation takes as input must be ready before applying the operator. And luckily, that is exactly what post-order traversals do. Let's try to execute the expression from the tree. We start at the top node, but since we are performing a post-order traversal, we do not apply the plus operation before all of its children have been executed. First child is minus. Again, we wait doing anything before all children are done. First child of minus is the value 15. That has no children, so we return 15. But we are still not done. The other child of minus is the value 5. No children of 5 either, so we return it, and now all children of minus have been evaluated, and the minus operation can be applied on its input, yielding 10 as the result. Now the minus operation is done. Next child of plus is the negation, but that node's only child is not done yet, so we need to handle that first. Plus has 3 children, and we cannot execute plus before these are done, so therefore we visit 2, which returns 2, 4, which returns 4, and 3, which returns 3. Now all children of plus are done, and plus can therefore be applied, yielding 9 as the result. The single child of the negation is now also done, so the negation can be applied, yielding -9 as the result. Finally, all children of plus are done, and the final result is then 1. So, we now know how to represent and handle all sorts of hierarchies in tree structures. Menu structures, nested lists, and various kinds of execution trees can be visualized in a user interface by traversing the tree in pre-order, and when the execution tree should be evaluated, we use a post-order traversal. In the example code that comes with the course, I have included examples of both the pre-order printing and post-order execution that we have just seen. We have done a lot of graph traversing in the past examples. The last one we shall look at is called breadth first search, or simply BFS. It can be thought of as a patient strategy where a newly discovered node is put in line and handled when it's that node's turn. BFS is useful for making exhaustive investigation of a graph from the origin node, completely finalizing one level at the time. It is also useful for finding each node's distance to some origin node, which again is useful for routing. We will traverse the graph using breadth first search and put a number on each node corresponding to the order in which the nodes are visited. Let's jump right at it and start the traversal from node A. Now we need a data structure to represent the line of nodes waiting to be handled, where DFS used a stack, which is a first in, last out structure. We will now use a queue, which is a first in, first out structure. So, node A's children B and C are enqueued, and the front element is dequeued in order to see what node to look at next. B it is. B has 2 descendants, namely D and E, which are both enqueued. Next node to look at is C. C has 2 children, namely E and F, which are both enqueued. Next node is D. D's only child is G, which is enqueued. E is next, and E has no children, so we proceed to the next node in the queue, which is E again. But E has already been labeled, and thus we dequeue the next node, namely F. F has 3 children, namely G, H, and I, which are all enqueued. Next node is G. G has no unlabeled children, so we proceed to the next node in the queue, which is G again. Nothing has changed since a few seconds ago, so we dequeue the next node, which is H. H has no children, so we dequeue again and proceed to I. The queue is now empty and we are done. Notice how the nodes have been labeled in a so-called level order, from the left to right, one level at a time. I think that's kind of a beautiful property.